In 2009, students at grades 4, 8, and 12 took the NAEP Science Assessment. During this exam, they responded to questions not only via paper and pencil, but also different science tasks, hands-on tasks, and interactive computer tasks. Through these tasks, students performed both real and simulated scientific experiments. Today, we will be focusing on this new generation of testing by exploring the types of tasks with which students were presented, how the students performed, and some common themes across the tasks. Approximately 2,000 4th, 8th, and 12th graders were assessed using the hands-on tasks at each grade. Students responded to two 40-minute tasks in each of the three grades. When doing these tasks, students were asked to perform real-world experiments and respond to data gathered and observations made. For the interactive computer tasks, approximately 2,000 4th, 8th, and 12th graders were assessed at each grade. Students responded to two 20-minute and one 40-minute task for each of the three grades assessed. They were presented with simulations of experiments that allowed them to demonstrate a broad range of skills involved in doing science. A computer-based setting also allowed us to bypass many of the logistical constraints associated with scientific experiments. For example, the passing of long periods of time or safety concerns. The samples of students assessed were separate from those in the paper and pencil 2009 NAEP Science Assessment. Results are available at the national level only. Student performance is reported in two ways: percentage correct on individual tasks and the percentage correct for all students across multiple tasks. In many classrooms, students routinely perform the kinds of tasks that now can be assessed through NAEP hands-on and interactive computer tasks. For example, 92% of 4th graders had a teacher who reported doing hands-on activities at least monthly, and 39% had a teacher who reported at least a moderate emphasis on developing scientific writing skills. Hands-on and interactive computer tasks routinely require students to write explanations of their conclusions based on evidence developed in the performance of the task. At grade 8, 98% had a teacher who reported doing hands-on activities at least monthly, while 57% had a teacher who reported at least a moderate emphasis on developing scientific writing skills. At grade 12, 51% of students reported designing a science experiment at least once every few weeks, while 28% said they wrote a science report at least once a week. Now, I'll describe an example of a hands-on task and an interactive computer task. Both the hands-on tasks and the interactive computer tasks include several different parts. For example, a single task can ask students to perform and respond to several different experiments. These experiments may contain several steps, and each of these steps may represent a student action of making predictions, observations, or explanations. Let's turn to the example tasks to see how these parts all fit together. Maintaining water systems is a grade 12 hands-on task. Students were asked to investigate the best site for building a new town based on the quality of the water supply. Students were given laboratory equipment and materials for performing experiments. They were instructed to test water samples and observe the levels of specific pollutants. And they were evaluated on their ability to present a reasonable, logical argument to support their choice of where to situate a new town. For the release website, we made a video to demonstrate this particular task. I'll be showing you pieces of the video to illustrate the steps of the task throughout this presentation. First, students were asked to predict, to make a preliminary recommendation for the site of a new town based on information about the quality of water sources.
The students go about the activity in stages. They use a kit that contains a map, reference charts, water samples, test strips, a stopwatch, safety gloves, and safety goggles, everything they need to perform their investigation. Using the reference materials in the kit, students are asked to form a preliminary recommendation about which site they think would be preferable for a new town. They must think about each site and the possible sources of pollution that surround it, like shopping malls, farms, or a coal mine.
"64% of students were able to explain their recommendations based on the materials provided in their kits. When we look at the breakdowns by gender, race, ethnicity, and eligibility for the National School Lunch Program, which provides a measure of family income, we see score differences for the various groups. This table doesn't indicate significant differences in performance for the groups, but we do have that information. For example, there was no significant difference in the performance of male and female students in this first part of the task. White and Asian Pacific Islander students had a higher percentage correct than Hispanic and Black students, and the percentage for Hispanic students was higher than that for Black students. In addition, students who were not eligible for the National School Lunch Program had a higher percentage than those who were eligible. We will see similar, though not identical, patterns on the individual performance items to follow. Because our samples here are smaller than on most NAEP assessments, particularly for the racial ethnic groups, differences that appear large may not in fact be statistically significant. Next, students performed water tests and evaluated data in comparison to national drinking water standards.
Once they complete their preliminary recommendation, the students then begin to test the water samples from both sites for levels of specific pollutants. Using the test strips and stopwatch provided in the kit, students perform a series of tests to determine the pH, copper, iron, and nitrate levels of each water sample. After they have repeated this procedure for both water samples, they compare the results to the colored reference charts and record their findings. Students need to determine whether the pollutants in the water samples from each site are higher than the national drinking water standards. The students are also asked to think about the possible sources of these pollutants and record their conclusions.
75% of students could make such observations and perform a straightforward investigation to test the water samples and accurately tabulate the data. Again, we see the percentage correct for the different student groups. On this step, white students had a higher percentage than the other three racial ethnic groups. Following their observations, students were then asked to make a final recommendation and explain their recommendations with data gathered in the experiment.
Using all of the information that they have gathered, students determine which site would be preferable for building the town and are then tasked to develop a scientific argument for their answer.
11% of students were able to do so. Once more, we see the variations in student performance, ranging from 3 to 17%. Students extended their inquiries by matching pollutants to specific water treatment processes.
They must then evaluate ways a water treatment plant could reduce or remove the pollutants.
14% of students were able to correctly evaluate the treatment steps and select those needed to reduce pollutant levels to meet national drinking water standards. Here, the percent correct ranged from 1 to 17% among the four racial ethnic groups shown. White and Asian Pacific Islander students had a higher percentage than Hispanic students. For statistical reasons, we could not compare the performance of Black students with that of the other student groups on this step of the task. In addition, students were asked to describe the processes used in water treatment by applying their knowledge of physical, chemical, and biological processes.
In addition to identifying the more suitable site, students must also explain which water treatment steps they think should be used to supply safe drinking water.
28% of students successfully completed this step of the task. Again, we see the range of performance across student groups. All of the steps we have shown made up the complete maintaining water systems hands-on task. In the sample interactive computer task we're presenting today, Mystery Plants, Grade 4 students designed and conducted 3 different experiments, with the difficulty increasing as they proceeded. They were given a series of simulations and asked to determine the following. What are the best sunlight conditions for growth for plant A sun-loving plant? What are the best sunlight conditions for growth for plant B, a shade-tolerant plant? What are the best fertilizer amounts for growth for plant A? For this presentation, we will be specifically focusing on Experiment 1, looking at the optimal amount of sunlight for a sun-loving plant. Students were asked questions that required them to use their prior knowledge to make predictions about plant growth under varying conditions. 4th graders were asked how much sunlight plants need to grow well. They were presented with 4 options, the correct one being that different kinds of plants need different amounts of sunlight to grow well. Students who chose this answer were given credit for showing complex prior knowledge. They were then shown a brief tutorial about how to perform the experiment, showing them the simulated greenhouse with various sunlight levels. "59% of students displayed complex prior knowledge, understanding that different plants have different sunlight needs." Once more, we see the percentages for different student groups, with a range from 47 to 67%. White and Asian Pacific Islander students had a higher percentage than the other 2 racial ethnic groups. Next, students were tasked with performing the experiment and making observations about the outcomes. This video depicts a student performing the experiment in which they observe how plant A's growth is affected by various amounts of sunlight. Students placed plant A in differing amounts of sunlight and observed how many flowers and leaves grew. They were able to see the growth results in the data table at the top of the screen, observing how the amount of sunlight corresponded to the growth of plant A. "80% of students correctly performed this step in Experiment 1. The range across groups was 74 to 86%. After making their investigations, students were required to select the correct conclusion for each investigation and provide an explanation for each. To provide a correct answer to this step, based on their observations, students had to choose that plant A was a sun-loving plant and support their decision. They used the information that they observed throughout the experiment, how different amounts of sunlight affected plant A's growth. 93% of students could identify that plant A was a sun-loving plant. 36% were able to support their conclusion with evidence from the experiment. The percentages of students able to support their conclusions ranged from 19 to 47%. White and Asian Pacific Islander students had a higher percentage than the other 2 groups, and Hispanic students had a higher percentage than black students. These steps collectively comprise Experiment 1 of the Mystery Plants task. When we look at how students performed across the 3 steps in Experiment 1, predict, observe, explain, we see some interesting patterns. For example, looking just at the 59% of students who showed complex prior knowledge in Step 1, if we follow the dark green circles to the right, we see that 49% both showed complex knowledge and correctly completed Step 2. And that 23% received complete credit on all 3 steps. However, 10% of students displayed complex knowledge but failed to complete Step 2 correctly, as shown by the small circle directly below the word observe. In addition, 8% displayed complex knowledge but failed to complete Step 2 correctly, and also failed to provide a complete answer for Step 3, as indicated by the small circle below the word explain. Below that is a very small circle indicating the 2% of students showing complex knowledge who failed to complete Step 2 correctly, but did provide a complete answer for Step 3. Now we'll look at the results for the 10% of students who showed no prior knowledge. Following the dark red circles from left to right, we see that despite a lack of prior knowledge, 8% of students performed the experiment correctly, and 2% of students could then go on to choose plant A as a sun-loving plant and explain their conclusion, as shown by the small circle at the lower right. When we looked at results for all 9 interactive computer tasks and all 6 hands-on tasks, we saw a few broad patterns or key discoveries. We have 3 key discoveries which we can look at in turn. First of all, we saw that students were likely to be successful on parts of investigations that involved limited sets of data and making straightforward observations of that data. For example, 84% of grade 8 students could use a simulated laboratory to test 2 soil samples in an interactive computer task called Playground Soil. 75% of 12th grade students could perform a similar investigation in the Maintaining Water Systems task. However, students were challenged by parts of investigations that contained more variables to manipulate or involved strategic decision-making to collect appropriate data. For example, in Experiment 3 of the Mystery Plants computer task, which we did not show, 35% of students could select from 9 fertilizer levels to test and determine correctly the level most conducive to the growth of a sun-loving plant. Similarly, 25% of grade 12 students could perform a challenging investigation on energy transfer, an interactive computer task that we haven't covered today, that asks students to investigate thermal energy transfer between substances to determine the better metal for a cooking pan. In addition, students could select correct conclusions from an investigation, but had difficulty when asked to explain their results. For example, in the mystery plant experiment that we just saw, while 93% of grade 4 students could identify that plant A was a sun-loving plant, only 36% could use evidence from their investigation to support that conclusion. Similarly, in a grade 8 interactive computer task, bottling honey, 88% of students selected the correct conclusion regarding an experiment involving the flow of liquids, while 54% could support their conclusion. This table provides a summary of the results used to support the 3 key discoveries we just mentioned. The table shows the minimum, maximum, and median % correct to demonstrate the ranges of student performances on the skills identified within each of the key discoveries. Also shown are the number of items across grades and assessment types. For example, there were a total of 12 hands-on and interactive computer tasks that reflected Key Discovery 1 and asked students to make straightforward observations. Students who were able to do so ranged from 42 to 94%. Here we see the percents correct across all tasks for students by grade across the hands-on and interactive computer tasks. For interactive computer tasks, the percentages were 42 for grade 4, 41 for grade 8, and 27 for grade 12. For hands-on tasks, the percentages were 47 for grade 4, 44 for grade 8, and 40 for grade 12. We also found a number of differences and some non-differences when comparing the performance of various student groups. For example, There was no score gap between white and Asian Pacific Islander students on the hands-on and interactive computer tasks. However, on the main science assessment, white students in grades 4 and 8 scored higher than Asian Pacific Islander students. When we compared male and female students, we found that female students outscored male students on the hands-on tasks, even though male students had a higher average score on the main science assessment. On the interactive computer tasks, male and female students scored about the same. During the assessment, we heard many enthusiastic comments about the hands-on and interactive computer tasks from students and NAEP coordinators. Some students found the tasks more exciting than a regular assessment, and coordinators felt this was generally true of the students they observed. As in any NAEP assessment, there will be much more information available online, including results and more information for all of the hands-on and interactive computer tasks. You will also be able to perform the tasks yourself.